Are you ready to learn printed circuit board design? I've been designing PCBs for 30 years, and I'm going to share my secrets with you.
Hi, I'm Stephen Chavez, Senior Product Marketing Manager for Siemens. Welcome to the third best practice video regarding PCB design, where we'll outline digital prototype-driven verification with regards to analysis as well as the domain specialist. Cutting out steps from the process, as well as having siloed team members, comes at a cost that directly translates to incurring higher risks. When it comes to digital prototype-driven verification, what really matters is eliminating prototyping with automated design reviews, evaluating multidiscipline trade-offs, and to empower design engineers with accessible technologies that reduce dependency on experts, and as well as co-optimization of silicon package and board systems. Out of all the years I've been designing boards, when it comes to analysis, I strongly feel this needs to be done. You can't skip these steps because it's going to bite you in the end. And especially the more complex our designs are getting, you definitely got to run the analysis, as well as shifting left on when you do the analysis and who is doing them. And so when we think about analysis or a digital prototype-driven verification, I look at it in two levels of running the analysis and then your domain specialist or your subject matter expert who's doing the analysis himself. Well, what are the problems that we see that we run into when it comes to an analysis is that a lot of respins are normalized because they've already accounted for 2 or 3 spins, and the pushback of running the analysis, oh, we'll do that next time. We'll push that off and we'll run it on the next revision. But right now, let's just hurry up and get it done so we can check the box and we get it done. The second problem you run into, and this refers to the domain specialist, is that your domain specialist tends to be working in a silo, or he's too far downstream by the time that analysis is ran. So there's 2 problems that we typically see when we talk about digital prototype verification. And when we talk about best practices and how to improve or optimize, we'll first look at analysis. You got to account for the analysis when you're first planning your projects. Don't skip it. Don't eliminate the analysis simply as you're trying to reduce project schedule and you're trying to reduce costs, because I guarantee you it's going to bite you in the end, especially if you're doing complex high-speed or RF microwave designs. You want to shift left that multidiscipline analysis when it comes to your schematic analysis, your thermal, like I said, signal integrity, power integrity, analog mixed signal analysis or AMS, your DFM or your design from manufacturing, and then your HAS testing, Halt testing, and DFT. You want to implement these all sooner in the project, so that way you're eliminating the errors before you're getting ready to release to fabrication or assembly. And this way you're designing quality into your design. You're not checking for quality after the fact. Now, when it comes to the domain specialist, you want to optimize multi-domain, so that way your specialist isn't isolated or becomes an afterthought. You want to utilize the domain specialist earlier in the process, rather than downstream. You want to bring him sooner in the design process, so you can do it concurrently or in parallel. You also want to utilize today's advanced capabilities within our tools, where you can do the analysis on the fly, and you can shift left the skill set on who's doing the analysis. Now, the value we're going to get from this is that, of course, you have reduced design cycle times, which relates to reduced cost. You'll remove potential for errors. You're designing quality in the design. You're not checking after the fact. And when I talk about removing potential for errors, you're removing them not just for fabrication, but you're removing them downstream. And even when you get into the lab and you're firing the board up, or when you get into your EMI testing, is the board going to pass? You'll have more potential for success if you're running the analysis up front. And of course, you always reduce respins. So now let's take a look at some examples of digital prototype-driven verification.
Verifying a schematic means fully inspecting all of the nets in a schematic. In Expedition, this is done by using an extensive component library of intelligent models, saving design teams hundreds of hours of manual efforts in visual inspection and lab debug time, leading to reduced project schedules and cost. This analysis is even able to validate signals across multiple boards in a system. Once complete, results are shown in an intelligent fashion to allow post-processing and enable quick fixes to any errors that are found. Locating critical issues is easy as users have the option to cross-probe back to their schematics to the problem area. Running simulation of critical signals on a board can save time later on in the design cycle. In the expedition flow, analysis can be done early on, even while teammates are finishing the work on other parts of the design. Simulating early allows teams to build constraints for critical nets so that issues can be avoided. Launching a simulation from the schematic is easy. In the case shown, the user is running a simulation on some DDR nets, specifically the DQ and DQS nets, so that he or she can provide accurate constraints to teammates. Using the DDR wizard means that the user has control of the parameters, such as how many bits will be simulated. Once the simulation is complete, an easy-to-read HTML report is created. This allows the user to see what lengths make sense to use as constraints that will satisfy both the data read and data write. With the simulations complete, the results as well as the constraint template can be provided to teammates for use in the defining constraints of the design. Once routing is complete in the design, an electrical rule check can be ran, helping users to identify any potential post-layout issues that may exist that would affect the signal integrity of design. Once a PCB has defined power planes and ICs have been placed and broken out, it's a good idea to run a DC drop analysis. Doing this earlier in the design process helps users verify that the power delivery is adequate and that issues like fan-out vias perforating the power planes have been avoided. In the example shown, a simulation is run on a plane that is used to supply power to the DDR4 DRAMs. Everything from voltage drop, via current, and current density can be verified and visualized within the tool. 2D and 3D views can be used to see where issues are in the plane, if any. Once the PCB is complete, this verification can be used as part of the final sign-off to make sure that nothing was missed. Exploring the thermal characteristics of a design can be done as soon as board 3D geometry is created, not necessarily when the design is complete. Thermally relevant information, such as fan velocity, if the system has a fan, and heat sinks are considered. Running the simulation of a board within the chassis of the product makes sure that the users get the most realistic results from the simulation run. Several different types of data can be extracted from analyzing the digital prototype. For instance, temperature distribution of the electrical and mechanical components, air velocity within the design, and even data about the temperature change over time can be captured, make it easy to optimize the thermal performance of the end product. Catching potential assembly and manufacturability issues early in the design process is essential to minimizing design respins. With Expedition, DFM analysis can be run from within a design layout. Users can fine-tune constraint sets to meet their needs. They also control which checks are run at each stage of the layout. Viewing the results of the DFM check is the same as checking the results of a DRC in the tool, and since the results are shown in layout, issues can quickly be addressed by cross-probing to the problem area of the board. Analysis can be run repeatedly at any time to make sure no new issues have been introduced and any that were found previously are resolved. This enables engineers to evaluate multidisciplinary trade-offs early in the design cycle, resulting in lower costs of testing and higher product reliability.
Thanks for tuning in. Next time we'll cover the best practices that include system-level model-based engineering.
When do you incorporate analysis into your design process? Comment below to start the discussion, and continue to follow along to learn more PCB design best practices.